Your mission, should you choose to accept it, is to understand how neurons communicate. Or an evil scientist will remove this information about the brain from the face of the planet. Put on the glasses to accept the mission. This device will self-destruct in 3, 2, 1.
The cell is the smallest living unit in organisms. We will focus on the nervous system, the network of cells and fibers that transmits impulses between body parts. The soma is the cell body. Dendrites are extensions which receive impulses and are the antennae of the cell. There is an axon, which conducts electrical impulses through the cell. The point where the soma meets the axon is the axon hillock. This is where the voltage-gated ion channels begin. The synapse is at the end, which is the junction between two cells. The cell has many organelles, including the neuron. Now you have the basis. Let's talk about the membrane. It is a phospholipid bilayer which forms a barrier to the water-soluble ions due to the hydrophilic heads and the hydrophobic tails, which stick together to form a barrier. The cytosol is not very conductive, so the axonal membrane has properties which enable it to conduct action potentials, or nerve impulses. Membrane potential is the voltage which describes the pressure to move charge over a distance. A resting membrane potential is a voltage across the membrane when the cell is at rest. The outside has more Na+, while the inside has more K+ and anions. Therefore, the inside of the cell is negative relative to the outside. Remember, ions are simply electrically charged atoms, and positive ions are cations, while negative ions are anions. Within the membrane, there are various passageways to create a flow of ions in and out of the cell when it is at rest. The two important channels are ion leaky channels and ion pumps. Potassium channels and sodium channels are separate, and they are each made up of 4 to 6 proteins, which assemble to form a pore. Ion pumps are enzymes that use energy to transport a specific ratio of ions across the membrane in each direction. This energy is released in the breakdown of ATP, which is produced in the mitochondria, the area of cellular respiration. ATP, adenosine triphosphate, is the energy currency of the cell, and it fuels many biochemical reactions. So, why do ions move across the membrane when it is at rest? Well, would you rather be in a tiny room with 50 people or 2 people? When it is less crowded, it is much easier to move around. Ions feel the same way. Resting membrane potential is negative 70 millivolts. Diffusion occurs through the leaky channels as ions move from a region of high to low concentration. This is also known as the concentration gradient. This is only one of 2 important forces. The other is electrostatic gradient. When diffusion is occurring, the potassium is being pushed out of the cell, so the inside becomes more negative relative to the exterior. The buildup of negative charge inside of the cell begins to attract positive ions who start to flow back in. This is the electrostatic gradient. When the concentration gradient and the electrostatic gradient begin to equalize because the same number of ions are moving in and out of the cell, the electrochemical gradient has been reached. To start off, the cell receives a signal or a stimulus in one of its dendrites. At this point, the cell is around negative 70 millivolts. It is negative because of the anions in the cell. This signal would be in the form of a ligand opening a sodium channel or a mechanically gated sodium channel opening. This would cause sodium ions to rush into the cell because the inside of the cell is negative and the sodium is positive. And you know what they say, opposites attract. The positive sodium ions entering the cell make the overall membrane potential more positive as it depolarizes. For an action potential to occur, the membrane potential of the cell would have to reach the threshold, which occurs at negative 55 millivolts. If the cell does not reach negative 55 millivolts and there is no action potential, this is called a gated potential, and the cell will return to negative 70 millivolts. If it does reach the threshold, an action potential will occur. Action potentials are either all or nothing because once the threshold is reached, the voltage-gated sodium ion channels will open and more sodium will quickly flood into the cell, causing rapid depolarization. These voltage-gated sodium channels are only open for about a millisecond before they are deactivated or plugged. This occurs at 35 millivolts. When the action potential starts, because the threshold is reached, the voltage-gated potassium channels also get activated, but there is a slight delay before they open, which occurs when the sodium ion channels close. When the potassium-gated ion channels open, the potassium rushes out of the cell. This is due to 2 factors. One is that potassium is positive, and because a bunch of sodium just rushed into the cell, the potassium is naturally drawn to an area that is less positive than the inside of the cell currently is, so it can, in a sense, relax a bit more. The other reason is that ions like to flow down their concentration gradients, and at this point in the action potential, the inside of the cell has a much higher percentage of potassium than the outside of the cell. After this peak of the action potential, the voltage begins to go down, and repolarization occurs in the cell.
When the potassium leaves the cell, it brings the voltage to around -80 to -90 millivolts, close to the resting ionic potential of potassium. This is called the undershoot. It is sort of like the rebound of the cell after becoming so positive, and is also known as the refractory period. At this point, the voltage-gated potassium channels close and the sodium-potassium pumps get to work, breaking down ATP to bring the cell back to its resting membrane potential by pumping sodium back out of the cell and potassium back into the cell. For every 3 sodium ions it pumps back out of the cell, it takes in 2 potassium ions. Action potentials move down the axon of the cell because as one part starts to go through an action potential, it changes the charge of the surrounding area of the axon, causing that area to reach the threshold and continue the movement of the action potential down the axon of the cell. There are little areas along the axon where there is no myelin sheath. These areas are called the nodes of Ranvier. The action potential changes the charge enough along the surface of the cell so that the area around each node of Ranvier is able to reach the threshold. The action potential basically jumps from one node of Ranvier to the next to continue the action potential. This is called saltatory conduction. Action potentials are all the same size, no matter the so-called size of the message being sent through the action potential. Action potentials communicate through the frequency at which they occur.
And voila! You may be wondering why this matters. Well, first of all, this never stops happening in your body. Neuron communication is how any message gets transmitted. For example, when you touch a hot pan, your neurons communicate so you remove your hand. There are many problems that can occur. Sometimes the process does not run completely smoothly, due to a plaque on the synapse, neurofibrillary tangles, or voltage-gated channels, and many other possible issues. 2 examples of diseases that would cause this are Alzheimer's or multiple sclerosis. Thanks for watching!